Hello and welcome to Direct Proofs. If you want to check out my Intro to Proofs video or some of my other videos on other types of proofs, I'll have them linked in the description hopefully. And if you want to just skip to the example section, that should be tagged in however they do it on YouTube. So recall that a lot of theorems are universal statements. Direct proofs are really helpful for that kind of theorem in general. And also a lot of theorems are if this, then that. So we call this part the hypothesis and that part the conclusion. So usually when we're doing a direct proof, we can say we assume the hypothesis to be true, and then we use some logic, maybe some arithmetic, to show that the conclusion follows from the assumption of the hypothesis. So for a general proof sketch, we'll state the theorem as we always do, and then if your theorem isn't written as an if-then statement, you can write it as an if-then statement just for yourself and for your reader. Next, we'll just state our definitions. So maybe you have some numbers that are odd, or maybe some numbers that are rational in here. So if your numbers are odd, then you would just say that number is equal to 2k plus 1 for some integer k. And if your numbers are rational, then you would say, oh, we can write them as j over k for some integers k and j where j isn't 0. Then we plug our definitions into the statement. So once again, if we were using maybe odd numbers, we would just say adding these two odd numbers together is the same thing as adding 2k plus 1 plus 2j plus 1 for some integers k and j. So sometimes you'll need to do some clever manipulations or some arithmetic on it. It depends on the problem. Sometimes you'll have to do more of those manipulations, and sometimes you'll have to do less of them. Finally, we come out with our conclusion, and we have shown that this is true. So let's review some of the basic axioms that we'll be using. So we talked about parity, which is odd and even, right? I'm just using these random letters, right? I could have used 2m to p plus 1. I could use some weird Greek letter, right? The main thing is that when you're making a proof that you try not to reuse letters that correspond to different variables. So then for rational numbers, a rational number is equal to g over h for some integers g and h where h isn't 0. And remember, we have to have the condition that h isn't 0 because otherwise it's not defined. Let's do some quick examples, first with just words. So if I live at Tulane, then I have been in New Orleans. So let's first define our things. So living at a place means that you have been there. And then Tulane is a place that is in New Orleans. Now let's plug all our definitions into our statement. So I say, I live at Tulane, which is our hypothesis, is equivalent to saying, I have been at a place that is in New Orleans. And if we look at that, that's obviously equivalent to our conclusion. So using just our assumption that the hypothesis was true, we've proven the conclusion. It's really important that when you're doing direct proofs that you don't assume that the conclusion is true and use it in your proof. We're really trying to build our conclusion out of our hypothesis. Let's do another example that actually uses numbers. So our theorem is the sum of two odd integers is always even. So if you can notice, this statement isn't actually written as if-then. So we can rewrite it, right? If two integers are odd, then their sum is even. And then it makes it a little bit easier for us when we're coming up with definitions. So let's state those definitions, right? Let m equals 2k plus 1 for k an integer, and let n equals 2j plus 1 for j also an integer. Remember, we don't want to use k in both definitions or j in both definitions because that's forcing them to be the same number. And then we plug our definitions into our statement. M plus n equals 2k plus 1 plus 2j plus 1. Then we do some manipulations, we do some arithmetic things, and then we eventually get that m plus n is equal to 2 times k plus j plus 1. Then we use a basic axiom to say that k plus j plus 1 is an integer because all of them are integers, and the integers are closed under addition. It may seem kind of tedious, but we do need to show that all those things are true. For our last example, let's look at some rational, irrational numbers. Our statement is the product of two rational numbers is always rational. Let's rewrite it as an if-then statement again. If two numbers are rational, then their product is rational. So another way to word it with quantifiers is, for all rational numbers m and n, m times n is a rational number. So once again, if you're looking at this, you don't necessarily have to rewrite your statements, much less rewrite them 2 times, but it can really help to give you a direction on where to start with your proof. So if we've rewritten it the second way now, it becomes really easy to write our definitions, because we can say that m equals j over k for jk some integers, k not equal to 0, and we can write n similarly right here, right? So once again, let's plug our definitions into our statement, do some manipulations, and once again keep in mind that we do need to say that both j times u and k times v are integers, because the integers are closed under multiplication, and that k times v is not equal to 0 because neither k nor v are equal to 0. Then we've basically come out with our conclusion, right? An integer divided by a non-zero integer is a rational number, which is exactly what we wanted to prove. Direct proofs are super useful, and a lot of the times it's the easiest to do a direct proof. Be sure to keep checking out the other videos about the other proofs though. See you!